So in the last 2 hours of this introduction course to data science, what I'm planning to do is teach you 2 techniques that are used in data science. There are 2 types of problems that data science tries to solve. One is called the function approximation problem, wherein you are given values for several inputs and there are several outputs that you want to predict based on those values. So what you're trying to do is you're trying to approximate the outputs as functions of input, and hence the name function approximation. So this is one type of problem that we routinely solve in data analysis. There is another type of problem that we also solve in data analytics, which is called the classification problem, where the idea is you have several different classes that you want to distinguish. You have data for each of this class that is given to you before, which is usually called the training data. So let's assume that you have 3 classes, then you say, okay, for class 1 I have this data where the input variables take these values. Similarly, you have data for class 2 and class 3. Now, given a new data point, I want to classify it as belonging to one of the pre-specified classes that we had, and this is called the classification problem. For example, one of the well-known classification problems that people now look at is what is called fraud detection. So if, let's say, there is a credit card transaction and there are certain characteristics of the transaction, and you are able to get transactions which are fraudulent and transactions which were not fraudulent, and you build a classifier based on this, when you get a new credit card transaction, you calculate these characteristics of the transaction and then you predict whether the transaction is fraudulent or not fraudulent. So this is a good example of a classification problem. Whereas if you have several variables in terms of, let's say, you're traveling from point A to point B, and someone has traveled from point A to point B many times, and there are several characteristics that can characterize this travel, and if you want to actually predict the time it would take for me to go from point A to point B using this various input variables. The input variables could be what mode of transport you have, what time of day, and so on. This would be a function approximation problem where you are actually looking for a specific answer and not a class. Now, what I am going to do is I am going to teach 2 techniques just to give you a brief idea about how you solve this function approximation and classification problems. Keep in mind that there are several techniques for each of these tasks, and we are just looking at something as a preliminary introduction to data science. So that is what I am going to do as far as today's class is concerned. After I do these 2 techniques, then we are going to teach a framework for solving data science problems, which will dovetail into a case study that you will be given, and that portion of this class will be taken by Dr. Hemant, who will teach you the framework that you can use to solve data analytics problems, and then also introduce a case study that you can solve. Now, before I proceed, would like to just make sure that if you have any questions from last Monday's class, I would be last Friday's class, I would be happy to answer those questions, and then we can proceed with what we're going to see today. So if you have any questions, please feel free to ask me from last week's class. I assume it's been uploaded. So if you've looked at the video and we have some questions, you can ask me and I'll be happy to answer. So I'll just give a brief pause and wait for questions. And in a minute or so, if there are no questions, I'll go ahead to talking about linear regression. Okay, since there does not seem to be any questions, let me continue with this course. So we're going to talk about linear regression. Linear regression or regression analysis in general is one of the most widely used statistical techniques. And as I mentioned before, the purpose is to build a functional relationship between dependent variables and independent variables. So I have a set of variables which needs to be predicted, and I have a set of variables which are used to predict those variables. Now the dependent variables are also known as response variables. They respond to changes to the input, or predicted variable, and these are usually denoted as variable y. The independent variables are known as predictor variable or regressor or exploratory variables, and these are denoted as variable x. So basically the idea is to build a model between y and x based on data that I already have for x and y, and when I get a new data for x, I should be able to say what the likely value of y will be. So that is the notion of function approximation. Now this type of problem is used everywhere, and you would have seen these kinds of problems in the engineering courses that you have seen or that you have learned. Now the regression analysis can be classified into many forms. The simplest is univariate versus multivariate. Univariate basically says that I have one output and one input, and I am predicting this output as a function of this one input. Multivariate would mean I have many inputs and many outputs that I am trying to predict for. Now the functional relationships can be classified as either linear or nonlinear. So if the relationship between the dependent and independent variables are linear, we call that linear regression, and if the relationship between the dependent and independent variables are nonlinear, we call that nonlinear regression. Keep in mind that when we talk about linear regression, there is only one particular form that we are using. The minute we talk about nonlinear regression, there are several forms that you can use. So nonlinearity could be cosine, exponential, hyperbolic, and so on. So there are so many nonlinearities to choose from. So nonlinear function approximation problems in general are much harder than linear function approximation problems. Regression analysis also characterized as simple versus multiple. Simple is one dependent and one dependent and multiple independent variables. So the difference between multiple and multivariate is that while the independent variables are multiple in both cases, in the multiple regression there is only one dependent variable. In multivariate regression there are multiple dependent variables. So you might think of multivariate regression as many multiple regression analysis that you perform. You just want to understand the difference between correlation and regression. So if I give you data like this, where the length of service calls y and the number of units repaired x, the plot goes like this, you can see that there is a relationship between y and x. And in fact, if you can eyeball this, you can actually say this is a linear relationship. And correlation would tell you whether these variables are correlated or not. In this case, they are positively correlated. What it means is as I increase x, y increases. So if you were to calculate Pearson's correlation coefficient, you will get a positive number, and rank coefficient, you get a positive number close to 1, which basically says there is a strong positive linear correlation between y and x. So regression analysis answers several questions. The first question is there a relationship between these variables at all? So if I give you y and x, is there a relationship or they are completely uncorrelated? What that would mean is I can never predict the output y based on the input variable values that I have. So is there a relationship is a question that regression analysis answers. It also answers questions regarding how strong is this relationship. It's a weak relationship or a strong relationship. Depending on the data, if there is a relationship, how accurately can we estimate these effects is another question regression analysis answers. How accurately can we predict future? And of course, in all of this, you can also ask, is the relationship linear or non-linear? So in linear regression methods, as we talked before, simple linear regression is the simplest of them all, where I have one dependent variable and one independent variable. And as we talked before, multiple linear regression would be where I have one dependent variable and multiple independent variables, and when I put many of these together, I'll get the multivariate regression. Now the way you solve this, there are many ways of solving this. One is called the weighted least squares. We'll get to that in a bit in this lecture. You can also do things like principal component regression, ridge regression, lasso, partial least squares and so on. These are more advanced versions of multivariate regression problems that you can solve. Now, in this very short introduction course, what we are going to look at is only simple linear regression. The other approaches are here as a list, and if you are really interested in this, I would strongly encourage you to go and look at how some of these are done. Nonlinear regression methods, there are many. I've just listed out polynomial regression and spline regression here. There are also methods called kernel methods, which have become very popular in the recent past. So the regression process is really an iterative process, and which is what is pointed out in this flowchart here. You start first and then you basically formulate the problem the way you've understood it. So you choose a set of variables which you are going to use to predict the dependent variable. You choose a model form. In the linear case, it is straightforward in terms of what the model form is. You find a method of fitting. There are many ways of fitting. You could do weighted least squares, you could do other forms of regression and so on. So you figure out a method of fitting that you're going to use. And in general, the method of fitting that you use would depend on the specific assumptions that you're making about the data, which would guide you into what method of fitting you use. So once you do that, you basically fit the model, and once you fit the model, then what you do is you validate the assumptions. The assumptions that you might have made, for example, the simplest assumption that this is a linear regression problem is something that you should validate. You might also have made assumptions about errors, which we'll come to presently. You have to validate those assumptions also. Here you have tools such as residual plot, outlier detection technique, sensitivity analysis and so on to validate assumptions. Now, if all the assumptions are validated and you have an OK, then you go ahead and evaluate the fitted model. When you evaluate the fitted model, what you do is you build your model on a partition of data which is called training data. You look at how well your model fits for data that it has not seen before, which is called the test data. And if your model does very well on the test data, then you stop and then say, look, I have a model that is well validated. All the assumptions that I made have been validated. Not only have the assumptions been validated, I have also been able to use this model to predict for data that the model had not seen before. So then you are ready to use the model for its intended purpose. If it is a no, you go back and start again in terms of formulating the problem. So when you go back here, depending on where you came from, you would make certain modifications to this formulation. For example, if the assumptions are not validated, you might actually go ahead and make other assumptions which will kind of tell you what method of fitting that you should use and so on. If this is a no, some of the things that you might think about is, do I have all the independent variables captured in my problem? Is the model form correct? And so on, or kinds of questions that you can use. So you have to remember that this process is a iterative process that you have to follow before you generate a model that is of use for its intended purpose. So let's take the same data that we had and then let's see whether there is a relationship between y and x for the data that we have here. So you might call this data as y and x, and if you have many samples, you might say I have data for several samples. In this case, I'm going to use I explain what the sample number is. So you could say yi, xi are data points for each sample, the ith sample. Now y1, x1 would mean when I had the independent variable value at x1, the dependent variable value was y1. Similarly, when the independent variable value is x2, the dependent variable was y2 and so on. So I have n such samples, and notice that we are talking about a univariate regression here because there is one variable that we are interested in, y, and there is one variable that we are interested in using to predict, which is x. When we talk about the model itself, till now we have talked about a linear model. But remember, in the previous lecture I said that most models will have what is called a deterministic part and the stochastic part, and the stochastic part is the one which you have no control over. It is random. What you basically do is you characterize the stochastic part using the distribution functions that we discussed in the last class, and then the total model becomes a combination of the deterministic part and the stochastic part. So if I were to write for each sample and a relationship between y and x, then I would have a deterministic part and a stochastic. Notice that the deterministic part explains y in terms of the independent variable. So what it says is, if you have a value for an independent variable, you multiply that by beta 1 and add another constant beta naught, that will give me the predictable component of yi, or the deterministic component of yi. On top of it, every sample there is an error that comes in, which is denoted by epsilon I, and this is the random part. In other words, we can never predict what this epsilon I is, right? So remember, in the last lecture I described saying, if you said what is the probability that this epsilon I will take a particular value, then I would say the probability is 0. However, if you were to ask this question, what is the probability that this epsilon I will take a value in a particular range, then you would be able to provide a probability for it. That's all you can do. So you can never exactly predict epsilon I. So that begs the following question, where for every sample point, if I had an epsilon I which is unknown, how would I ever calculate beta naught and beta 1? Because for every data point that I get, there is an epsilon I that is unpredictable. So the way regression analysis works around this problem is the following. What you do is you write this error in this form and then say, I want to fit parameters beta naught and beta 1 in such a way that the sum of squares error for all the samples put together is minimized. So that's the way regression looks at it. So if you look at this expression, what it says is sigma I epsilon I squared. So if I had n data point, for the first data point I would get an epsilon 1, which would be y1 minus beta naught minus beta 1 x1. Similarly, I will get epsilon 2, epsilon 3 all the way up to epsilon n, and this expression will be epsilon 1 squared plus epsilon 2 squared all the way up to epsilon n squared. So in some sense, I am trying to reduce the sum of squares, and what do I have here to reduce the sum of squares? Ya is fixed, remember, that's from the data. Xi is also fixed, that is from the data. So the only tuning parameters that I can use to minimize this are beta naught and beta 1, and the values of beta naught and beta 1 which minimizes this is called the sum of squares, least sum of squares estimate for beta naught, beta 1. Now these are the formulae that you can get after analytically minimizing this as a function of beta naught and beta 1. And again here I like to point out that in the fundamentals for data science class last week that I mentioned linear algebra, statistics and optimization as key components. You already see the notion of statistics and distributions come here in terms of epsilon I, and the notion of optimization comes here in your calculation of beta naught hat and beta 1 hat. Now pictorially what this means is that if I draw this line beta naught plus beta 1 x, then that would be the blue line. So you notice that you take the data and the fit is in some sense the best fit linear line that characterizes all these points. Remember, if I were to draw a line, I have only two parameters to work with. So if I have n data points, it would be impossible for me to draw a line that will go through all the points. So what happens is this line goes in some sense where all the data is represented to the best possible manner. Now you might ask what this error is. This error is basically the error that one sees in each of these data points. So this is the error here, this is the error here, this is the error here, and so on. So when you minimize all of those errors, then you get your beta naught and beta 1. So this is the basic notion of least squares regression. Now you might wonder as to why I have to use a squared here. Why not use just epsilon 1 plus epsilon 2 all the way up to epsilon n. This is obvious because if I were to use something like this, I could have a very large positive value, very large negative value, followed by very large positive, very large negative, and the sum will go to 0. It will be minimum error, but the fit would be very poor. So if I were to just use epsilon 1, epsilon 2 and so on, it's a problem. So that's the reason why we end up using epsilon 1 squared plus epsilon 2 squared all the way up to epsilon n squared. There are other options for this. For example, you could use something like sigma I, absolute value of epsilon I is something that you can use. Here, whether it's positive or negative, this will become positive. So if this whole term is 0, then individual errors will have to be 0. This is what is called L1 norm, and you could do regression based on this norm also, just for you to know this. But in general, when someone talks about sum of squares error, this is the objective function that one is used. So once you fit the model, then what you can do is you can predict independent variable based on the independent variable value. So if I had y1 x1, now the regression model is beta naught hat plus beta 1 hat xi. So if you want to predict a value for y1, then you will write this as y1 hat equals to beta naught hat plus beta 1 hat x1. So notice that this y1 is actual data, x1 is actual data. What we are assuming here is there is no error in x1, so that it can go into this model, and based on the value of x1 I am going to predict a y1, and clearly this y1 and y1 hat will not be the same. So there will be a minor difference, and that is the error in your prediction. So how do I know whether I have a good prediction? So there is something called an R squared. The formula is here, and since you have the slides, you can look at this formula. Typically, R squared values will be between 0 and 1. 0 would indicate very poor fitting, and 1 would indicate very good fitting. So if you have an R squared of very close to 1, that basically means that your model is doing a very good job. Now there is also something called adjusted R squared, which basically takes into account the number of parameters that you are using in fitting your model. So it directly takes into account that if you use more number of parameters, it will penalize it somehow, and it will adjust the R squared so that everything is normalized. But in general, R squared, you want it to be as close as 1 as possible for best fitting. Now once you do this, when we are building this model, yi is beta naught plus beta 1 xi plus epsilon I, and when we are doing the least squares fitting, there are certain assumptions that we are making in terms of the distribution of this epsilon I. The error distribution is assumed to be normal. We are also assumed the errors are uncorrelated. So these are underlying assumptions that are made when we were doing this least squares estimation as described in the last slide. So one thing that you could do for looking at goodness of fit is, over and above the R squared, one could also look at the epsilon itself that is obtained, and then see whether that is consistent with the assumptions that we have made when we did the regression analysis. Now let's assume the true model between y and x is really beta naught plus beta 1x. You have now a value for beta and beta 1. Clearly this and this will not be exactly the same, because this is a true model, and this beta naught and beta 1 that you have estimated now is based on limited amount of data that you have. You don't have all the data. Not only that, there is also error in the measurement, so that is going to corrupt the estimates that you have for beta naught and beta 1. So that is the reason why, instead of saying when we use regression to estimate beta naught and beta 1, we don't use the beta naught and beta 1 symbols here, but we use symbols with hat on the top. The symbols hat distinguish that this is not the true beta naught and beta 1, but this is the best estimate that we could make for beta naught and beta 1 at this time. So that's why I have this beta naught hat and beta 1 hat. Now there are some terms that are used for what is called the ordinary least squares. So what is ordinary least squares? if I have y and x, notice when I write the equations, I write yi is beta naught plus beta 1 xi plus epsilon I. So this basically assumes that whatever measurement I get or whatever is the dependent variable, it has error. However, we are assuming the independent variable x is actually the correct value, or there is no error in the independent variable. So this is called the ordinary least squares. You could also make an assumption where you say if I have data y and x, you could say I have errors both in my dependent variable and independent variable. If you use that assumption and try to solve the same problem, that is called as TLS. T stands for total. So this is called total least squares. Whereas whatever we have described till now is what is called ordinary least. Now the estimates are beta naught hat and beta 1 hat, and what you are interested in is certain properties that go with this estimation. So you want both beta naught hat and beta 1 hat estimates to be unbiased. So which is written in this way. It says the expected value for beta naught hat is beta naught and the expected value of beta 1 hat is beta 1. So in other words, in a layman terms, if you want to understand this, if we were to calculate this beta naught hat and beta 1 hat with different data sets, multiple number of times, let's say infinite number of times, and then we were to average all of these values that we have, then we want that average to be equal to the truth. So that is what this expectation says in terms of layman terms. Whenever I say an estimate, I say okay, it will be unbiased, but if I give you a value, you are also interested in knowing how far away from the truth would this be. And remember, in the last lecture we described this as what a variance shows. So the variance of estimates can also be calculated using this formula. This basically says how much variability is this likely to have from the truth. The smaller the number, the better it is. Again, smaller the number, the better it is. So these are properties of OLS that one is interested in. Now you might ask, if you give me a beta naught value, can you also give me some bounds on this, some confidence that you have for this, right? So I give you a beta naught hat and I also give you a beta 1 hat. So your interest might be in saying, okay, don't only give me this value, but give me a limit where this value is likely to lie. These are called confidence intervals. Now you can ask for confidence interval at different levels of significance. So if we ask for confidence interval at 5% level of significance, or you could have a confidence interval at 10% level of significance and so on. Those are given by these formulas. These are easy to calculate. What you need to do is you need to look up a table for t statistic, which we talked about in the last class, and then depending on your level of confidence, you will choose this number, which will be an area under the curve, and depending on the number of data points you will have a certain degree of freedom which you'll use to calculate this t. And once you have this, you can give confidence intervals on these beta 1 and beta naught. Now that you have built a model, the next logical question that you might have is the following: is the fitted model adequate? Adequate in the sense, is it doing well? You could also ask, is it more than necessary, right? So is it good, and is it something which I can reduce further? So there are two ways of answering this question. One is, in the previous case we said, okay, I can give a confidence limit on beta naught hat and beta 1 hat. So in some sense I can test the significance of these individual coefficients beta hat and then use that test to figure out whether I need beta naught and beta 1. Another thing that you could do is you could build two models. One is a reduced model and another one is a full model, and then you can do a test to check whether the full model is giving you any extra information over the reduced model. So this can be done using hypothesis testing. So let's illustrate this here. So for example, if you have a reduced model which is y hat beta naught plus epsilon I, here what we are saying is the slope is not significant. So in other words, what we are saying is, if you draw a straight line, average value, that itself explains the data. So let me contrast this. Supposing you have y and x, and if your data is like this, and in another case, let's say your data is like this, then in this case maybe you can draw a straight line and then say this itself captures the data. There is no need for a slope here, whereas in this case you might need a slope. So how would you find out from purely data which is the case? Do I really need this term here or not? Is a question that we might be interested in asking. So what you do here is you calculate certain terms here. One is called the sum of squared error, and the calculation and the corresponding picture as to how you do the calculation is shown here. Due to the fact that we have more things to cover, I'm just going to let you look at it and then look at the slides later to understand each of these terms. But basically you calculate three sum of square errors. One is sum of square error, sum of square residual, and this is called sum of square total as defined here. Once you calculate these, then you can actually do what is called an F test to figure out whether the full model gives you any more information. So the F test statistic in this case, what you can do is you can take the numerator to be sum of squared residual, the denominator to be sum of squared error divided by n minus 2, and based on a certain level of significance, like what we discussed in the previous case, we run a test statistic, and if this test statistic passes, then we say the full model has extra information. If the test statistic fails, then we say the full model does not have any extra information. Remember, now you see how important statistics is. In the last class, we talked about hypothesis test, how we talked about picking a distribution that you have to use based on what is the test you are going to do. So in this case, the distribution that we looked at is the F distribution. And once we have an F distribution that we are interested in, there is a global F distribution that we are interested in, and we have to actually calculate the test statistic from the data, and then you compare the test statistic from the data to your global distribution, how it's supposed to look, and this test gives you a hypothesis test where you can either accept or reject the null hypothesis. So here are some runs from R programming to get some of these numbers. I'm going to skip these, but you can do this in Excel, any other package that you are comfortable with, MATLAB and so on. So in summary, I have shown one example of a function approximation problem, which is linear regression, shown how we can use linear regression to predict the dependent variable as a function of independent variable. And this also illustrates nicely that all the concepts that you have learned in terms of statistics, in terms of linear algebra, and in terms of optimization, how they are all important, and they form an inherent part of data science algorithms. In this case, we saw that optimization is used directly when we are trying to minimize the sum of squared error. So in that case, the objective function is the sum of squared error. There are no constraints, and the decision variables are beta naught and beta 1, and you can basically set it up as an optimization problem and solve it and get the expressions that I showed in the slide. So that's where optimization comes into picture. Now once you fit the model, you have several questions in terms of, is the model good enough for me to work with? And you might say, is this model the most parsimonious model that I can get? In other words, have I added terms that are not making much of a difference in terms of prediction? So we saw statistics is a tool that you should use to answer such questions. So it kind of nicely brings in how the basic fundamentals are all important for function approximation. I just want you to remember that what we have seen here, because of the short duration of this course, is just one type of regression, which is a simple regression where I have only one independent variable and one dependent variable. More complicated regression can be done if you are looking at multivariate regression, where you have multiple independent variables and multiple dependent variables. Also keep in mind that we have looked at only sum of squared errors, and as I pointed out before, you could do the same regression problem using L1 norm, where instead of squares you take the absolute values of errors and then minimize that, and also that there are multiple nonlinear functions that you could use for doing this regression, which are called nonlinear regression models, and we have not discussed those, but those might become very important if the underlying data that you are trying to capture has nonlinear relationships. So this gives you a brief glimpse into one of the activities of data science, which is function approximation. What we are going to do next is we are going to look at another technique for classification. It will give you an idea of how classification techniques work, and then Dr. Hemant will come and discuss a framework for solving data analytics problems. So I'm going to give you guys a few minutes to think about and ask any questions that you might have from either the previous classes or today's class, and after those few minutes, after we answer questions, or if there are no questions, we will start again on this k nearest neighbor. There is a question that has come which says, what is overfitting? It's a very interesting question. If you were to look at this data that we have here, I will go to a previous slide so that you can see this here. If I have this data here, now if you just look at it, you would say, look, it looks linear, so I'm going to fit a linear model, in which case you're going to draw something like this in the middle. Now the number of parameters that you're going to use to fit this data is basically only 2, right? So I have y equals beta naught plus beta 1x. So I have these 2 parameters and then I fit this. Now if this model, which is a straight line, explains this data well, then we have said this model does a good job. Now if, let's say, you are not happy with the fact that this point, this point, this point, this point, these points are not exactly sitting on the model. So when you look at the error for individual data points, you will see that there will be a slight error for this, there might not be any error here, but there will be an error for this point, and so on. So you say, look, I do not want that error, so I want to reduce it. So how would I do it? So the way I do it is add more parameters. So for example, I can say I'll take a next level of model, which is beta 1x and beta 2x squared. When I do a model like this, now I have not a linear but a quadratic, and the quadratic will fit the data little more. And if you keep doing this process, if you have n data points and you fit a model, let's say with n parameters, let's say I have 4 data points, then I could say I will do a beta naught plus beta 1x plus beta 2x squared plus beta 3x cubed. Okay, and I can fit the data for beta naught, beta 1, beta 2, beta 3. Now I have a lot more parameters, the error has come down, but if you look at your model, what will happen is your model will start doing this. So your model will do this. So if the truth were really the straight line, what your model is doing is it is fitting every data point exactly, but it has not got the most important feature of the data. So in other words, if the data were truly on a straight line, but these changes that you see in the data are really due to noise or error, what you have done is you have fitted the noise with more parameters. And fitting noise with more parameters is what is usually called as overfitting. If you want any more clarifications on overfitting, please feel free to write. If this is clear, if there are other questions, I will be happy to answer. If not, we will take a short break and then move on to k nearest neighbor clustering. So there is another question that has come in, which is, how do you know which model is suitable for the given data? That's a very interesting question, and that's not a very simple question to answer. So what you do is you do various tests. For example, whenever you get data, you break it into training and test data. And then what you do is, as a first cut approximation, you might say the model is linear. So I'm going to fit a linear model between the inputs and outputs. And you're also going to make some assumptions about the errors that are there. You might say these errors are uncorrelated, they are Gaussian, and so on. and then you fit a model. Now once you fit a model, the immediate diagnostic that you have is this R squared. If this R square is very poor, that is very far away from 1, then you automatically know even for your training data that this model is not doing well. In which case you will say, look, there is something wrong with one of the two assumptions, which is either my noise assumption is not right, or my model assumption that it is linear is not right, or in the worst case there are other inputs that are important which I have not taken into account. So you could have any of these problems. Now if your R squared is good for the training data, then you would do tests on the errors that you have estimated. How do you get the error you have estimated? You have a y value and you have a y predicted value. If you take a difference between these two, you will get the errors. And then you look at it and then say, I made certain assumptions about noise. Does this error follow those assumptions? If that follows the assumption, then your second diagnostic is also passing. Then what you will do is you will actually really go ahead and do the real test, which is take test data and then see whether your model predicts well on the test data. In many cases, this is where you have problems. So what you do is, if your test data is also predicted well, then given whatever information you have, this is the best you can do. You live with your model. If your test data, the model does very poorly, then you go back and basically you have to ask 3 questions regarding your model. Do you have all the effects captured in the model? What this means is, if there are several independent variables that affect my dependent variable, do I have data for all my independent variables is something that you should worry about. The other thing you should worry about is whether the relationship is something that you are capturing correctly. If it's linear, it's fine. If it's non-linear, how do you capture that non-linearity? And the third thing is, are your assumptions about the noise characteristics the same? So in this field of data analytics, this is where statistics, optimization and advanced concepts come together for you to be able to do this in an iterative process and come to a stage where both on training and test you do well, and that's the model you choose. So that is the answer to the question, and this is in fact the crux of all of function approximation problems, where how do you avoid overfitting? This is a question that was asked before. How do you figure out the best functional representation that describes this data? That's another important question that you need to answer. So while you can go through these steps, there's still some idea of your knowledge about the process which would let you make some judgments and come up with the best model. So short answer is, if your model does very well on training and test data, then it is suitable. If it is not, you have to go through this process till this happens. Is this okay? Do you need any more ideas to be clarified? Okay, if not, then we'll go on to another data analytics technique. Now it's very interesting that this is a very simple technique for a slightly different type of problem, which is what I talked about at the beginning of this class, which is the classification problem. While k nearest neighbor can be used for both classification and function approximation, it is used largely in classification problems. I am going to explain what k nearest neighbor does. So k nearest neighbor is what is called a non-parametric method used for classification. So let's understand what this word non-parametric means. In the linear regression that we just described, if you look at the way we approach the problem, you might have, let's say, 100 samples or 200 samples or 10 samples, whatever might be the number of samples you have. Ultimately, what you get out of that data is a model, and in the linear regression case, that model had 2 parameters. So in other words, you might think of this as having parameterized the data with just 2 parameters. So that is called a parametric model, whereas we will see that k nearest neighbor has no parameter that describes the data. There are some parameters which are used to tune the algorithm, but we want to distinguish that from parameters that are used to describe the data itself. So there will be no parameters that are used to describe the data. That's why it's called a non-parametric method. It is a lazy learning algorithm where all computation is deferred until classification. In other words, once you give the data, the k nearest neighbor algorithm does not do anything. It just waits, and when you query it and ask a question, that's when it does computations to do the classification. So remember, I mentioned what classification problems are. Given data for different classes, I want to be able to point out to what class a new data belongs whenever I get new data. So that is basically the notion of classification problem. Now there is something called a binary classification problem where the number of classes are just 2. I gave an example in the last class for the people who were in the last class. I said if you want to classify someone and then say would this person like South Indian food or North Indian food, that's a binary classification problem. Now if you make that more sophisticated and then you say look, with this guy like South Indian food, North Indian food, Chinese food, Italian food, then there are multiple classes into which you are binning that person, right? So typically classification problems are multi-class. A simple form of a classification problem is what is called binary classification problem. Now coming back to KNN, we said it's a lazy learning algorithm. It is also an instant based learning algorithm where the function is approximated locally. So this is a little more complicated. I will have some graphs and pictures in the next few slides which will illuminate this much more easily. So we will wait till we see how the algorithm works. Now KNN is a very simple algorithm. It's very easy to implement and it's used in quite a few applications because of the fact that it is very simple. There is no training and test phase. Typically whenever you do machine learning algorithms, there is something called a training phase where you get the data and then train your algorithm on the data, and then whenever new data comes you test that new data and then either classify or do function approximation. In KNN you are ready to use this algorithm as soon as you have the data. There is no explicit training and testing that is required. So when does one use this algorithm? When there are nonlinear decision boundaries in classes and when the amount of data is really large and you do not want to run very sophisticated optimization algorithms to do parameter estimation from this data and so on. Since all the computation is reserved till the actual classification, it makes it possible for one to use this algorithm with large amount of data. But keep in mind that when we use this with large amount of data, there are other issues that will come up. So one has to really think about how do you partition the data so that you do KNN effectively and so on. So this is what I mentioned in the very first class of this course where I talked about map reduce concepts and so on. So you can use some of those ideas also in combination with KNN algorithm. So for KNN the input features can be both quantitative and qualitative. The outputs are categorical values which are typically the classes of the data. So for example, if it's a binary classification problem, I could have many inputs and the output could be 0 or 1. You could say if the output is 0 it belongs to class 1, and if the output is 1 it belongs to class 2 and so on. So I would say the output is a categorical variable. KNN works very simply by explaining what the output is likely to be by simply counting how many people around that point do the same thing. So very simple idea is you might say if you went to a particular region, let's say Chettinad region, and then say how many people will love Chettinad food, right? So if you take people around that region and then say what type of food they like, most of them will like Chettinad food. So it's very easy to say they love Chettinad food, right? So in some sense, your neighbors, their preferences are likely to be your preference is the notion that we are going to use. So this is the simple idea that KNN uses. So because it's non-parametric and because it just is going to count what the neighbors are saying, the algorithm does not make any assumptions about underlying data distribution and so on. So you don't have to assume it's normally distributed or chi-square distribution and so on. None of those assumptions that you need to make. The only parameter that you choose is the parameter k, and remember the distinction I made. This is a tuning parameter. This is not a parameter that is derived out of the data to explain the data. So this is tuning. So I can say k is 1 or 2 and run a KNN. right? So that slight distinction you have to remember. So there's still not a parametric method, it's a non-parametric method. It also requires what is called a distance metric to do the classification, and there are many types of distance metrics that are used. There is something called Euclidean distance, Mahalanobis distance, Hamming distance, and so on. So these are various distance metrics that you can use. You can easily look up what these are in the internet. So the KNN classification is basically performed using the following 4 steps. The first step is to compute the distance metric between the test data point and all the labeled data points. So what we are saying here is, if I give a data point and I have many other data points for which I have class labels. So this I say is class 1, this is class 2, class 1, class 1, class 1. What you do is you find the distance between this point and every other point. So this is the first step. What you do is you order these points in terms of the distances. The lowest is the first and the farthest is the last, right? So if you take a point and then from that point you take every other labeled point and find the distance, and then you say I am going to order these data points in terms of the point that is closest to the test point to the point that is farthest to the test point. And once you have ordered this, then you take the top k data points. So if k is 3, then you take the top 3 data points. What are these data points? These are the 3 closest data points to the test data that you have. Now if you are doing a binary classification problem and of these 3 data points all of them say that they belong to class 1, then you say the test data also belongs to class 1. If 2 of them say they belong to class 1, you say the test also belongs to class 1. If only one says it belongs to class 1, then you say test belongs to class 2. And if none of them belong to class 1, you still say the test belongs to class 2. So it's a very simple idea that you use. So in terms of this picture here, if you notice, depending on k is 3 or 5 and so on. So supposing you have, let's say, a new test data point that is here. If k is 3, then what you do is you find the 3 data points that are closest to it, which happen to be this, this and this, and you look at them and then say 2 of these say they belong to the class 2 and 1 belongs to class 1. So I would say this test point belongs to class 2. If you had to put in a point here, then the 3 closest points are these and all of them belong to class 1. So I will say the test point also belongs to class 1. Now if you were to say k is not 3 but k is 5, then you take 5 closest points. So for example, if I have a point here, then I take the 5 closest points, of which 3 belong to class 2, 2 belong to class 1. So I will say this point belongs to class 2. Now notice how beautifully this separates a nonlinear boundary. So if I were to draw a classifier for this and I want to draw a perfect classifier, I have to do something really crazy like this. So this is the boundary that will really separate all the red points from blue points. Now if you give the data and then ask an algorithm to find a boundary like this, any algorithm will find it very hard to find boundary like this, whereas k nearest neighbor using a very intuitive idea will be able to solve this problem quite effectively. So this is what I illustrated in the previous slide. So when you use KNN algorithm, there are certain things that you need to be aware of. You have to choose the correct k and that gives you the best result. Typically what is done is the algorithm is run for different k's and then whatever gives me the best solution is chosen as the k that I am going to use. You have to keep in mind that noise has a big effect in terms of the performance, and when you have many features, then there are 2 problems. One is that the calculations of distance can become complicated, and the other problem is there might be features which are redundant, which have an impact in terms of the classification, because while they add to the distance, they have no information value. So it's important to remove redundant features when you use KNN algorithms, which is what I have talked about in terms of parameter selection and feature selection and scaling. Okay, so this is a classification problem, a very simple algorithm which can be used to do a classification problem. Now more sophisticated forms of these algorithms are when things like k-means clustering, fuzzy clustering, spectral clustering and so on. So there are many clustering techniques that are available, This is the simplest technique called KNN that one can use to do classification problem. So what we have tried to do here is, in the 6-hour lecture, we at the very least wanted you to get an appreciation for what is data analytics, what is big data, some applications of where it has been used. This was the first 2 hours. The second 2 hours was a little heavy and maybe a little dense, because we tried to teach linear algebra, statistics and optimization in 2 hours, which is simply not possible. So the idea there was for you to understand that the notion of rank and null space and things like that are very important from a linear algebra viewpoint. The idea of distributions and hypothesis testing are critical when you think about statistics for data science. And then all machine learning algorithms can be thought of as really optimization algorithms. So that's the idea that we wanted to give in the second 2 hours. In the last 2 hours, we wanted to show you one technique each for 2 different types of problems. One is called the function approximation problem, another one is called the classification problem. While doing this, we also emphasize that all the fundamentals that we talked about are all important, and they form a major part of any solution technique that you have. Finally, what we are going to do is we are going to do what is called a guided thought process for solving data analysis problems. Dr. Hemant will go through this, and then you will also describe a case study which you will be working on other than the assignment problems that you will be given. So once you do those, you will get graded and so on. Okay. So I am going to stop here. Hope you found these 5 odd hours of material on data science useful, and feel free to send your questions if you have any, and it will get forwarded to me, and I can answer that through whatever support network there is for answering questions. So I am going to wait for a couple of minutes to see if there are any questions. If there are not, I will take a short 2-minute break, and Dr. Hemant will continue with the course. So there is a question, can you please give any real-time application where we can use KNN algorithm? Any classification problem that you have, you can try and apply KNN algorithm. Because it's very, very simple, it's very easy to implement. So for example, if you have a process plant and then you have data for normal and abnormal regions, you could use a KNN algorithm to kind of look at the data and distinguish between normal and abnormal regions and so on. So in fact, this is probably the very first simplest algorithm that you could try, and if this works well, I think you do not have to go for other algorithms. But keep in mind that when you really apply KNN real time for very large data sets, then the simple implementation might be a problem. This is because of what we said in the algorithm, where you have to find the distance between your test point and every other point. So it might be much more complicated if you have a lot more data points, because online real time you have to do many computations. That's where there are these map reduce versions of this KNN algorithm, where you can actually do it real time, where you can make sure that you get the right answer, but in a very short time. If not, I will hand over the class to Dr. Hemant.
Good afternoon, everyone. So we have seen Professor Raghu's 5-hour course on the data analytics. What we are going to do this 1 hour from now is to see a framework in which the data analytics problems are solved, and we will also give an example where we solve one problem, which is data imputation problem, and which is the problem which you are going to solve for your project also. What I am going to do in the next 1 hour is I will introduce you to the framework in solving the data analytics problem and give an example of data imputation problem, and introduce you to the project problem statement and what is expected from you to in terms of the project for this course. Let's move ahead. So this is the conceptual framework for solving data analytics problems. So we have divided it into like 6 steps, and it is an iterative process. The first step is the problem arrival, where we have whole lot of words and we don't know what exactly we can do, which is the problem statement is kind of diffuse words, which means somebody comes to you or a client comes to you, gives you data, and then you have to, so they will ask, what can be done with this data? There are several things that we can do with that data. We have to actually figure out what could be done, which is step 1. Step 1 is problem definition. Convert that loose words into one problem statement which is as precise as possible. In the sense, so we have to discuss with the client, you ask his requirements and then see what we can get from this data, and then formulate or convert this whole lot of words into a single precise problem statement. This is the first step in data analytics problem, and which is the most time taking one also. That's because you will have whole lot of data, and based on the requirements we need to assess whether we can answer that questions from the data, and based on that we need to arrive at the problem definition. Second step is problem characterization. When you say problem characterization, what do you mean is, how do you want to solve this first problem that is defined in, how do you go about solving the problem that is defined in this step 1? So what are the steps, what are the high level problems you are going to solve, and what are the sub problems, and in each of the sub problems that comes in this high level programs, and what is the granularity you want to maintain in solving this high level problems. And we make some dependence diagram. Let's say we solve the class 1 first problem and then move ahead. This is kind of identify the problems and sub problems as we have seen that there are two types of data analytics problems, that are function approximation and classification problems. You identify this high level problems and the sub problems as either function approximation problems or the classification problems. Once you do that, the next step is the solution conceptualization. We have seen one method each for this function approximation problem and the classification problem, which are linear regression and the KNN. Depending upon the number of sub-problems you have and the data that comes with the sub-problems, you need to choose appropriate function approximation technique or the classification problem technique to solve those sub-problems and the top-level problems. So in this solution conceptualization, what we do is, we are thinking about the solution processes, list out all the assumptions that go in solving that particular problem and the flow chart for solving these problems, and you represent kind of the steps in a complete flow chart. How are you going to solve this problem? Once you identify the solution conceptualization for the problems which are either classified as function approximation problems or the classification problems, you need to identify the method in which you are going to solve. So this step involves mapping the elements of this flow chart and pictures into mathematical models. By this we mean, so in each step of this flow chart, which technique are you going to use? What is the solution that it comes from this each picture of this flow chart? And then the next step is actualization. You have figured out what technique to use. Now the step 5 is really solving the problem using the particular tool that is being used. So you solve that problem and then see your results. Once you get the results, as we are mentioning in the linear regression, simple linear regression problem, we need to assess your assumptions, and then if you are okay with the accuracy of your model, you will stop. Otherwise, you will go back to your assumptions which are in the step 3 and go back and change your solution conceptualization and accordingly choose your methods and apply it again. That means we are repeating the steps 3 to 6 if necessary. You go through this iterative procedure until you obtain the solution for the problem to a satisfactory level. So if you want to summarize, this is how a flowchart for solving data analytics problems looks like. You'll start with problem statement or the data. So given the data, you will come up, the first step is, this is step 1. The first step is coming up with the problem statement, that is one precise statement of the problem. The second step is problem conceptualization, where we divide the problem into sub-problems that is needed to be solved, and you build in the dependency diagram, how are these sub-problems related and how solving the sub-problems will help in solving the top level program, and classify this each sub-problem or the top level problems as either classification or function approximation problems. So once you do this problem conceptualization, next one is the solution conceptualization. Depending upon whether you want to solve a classification problem or function approximation problem, you need to write the assumptions and what are the steps involved in those problems. You need to put it in a form of flowchart and pictures. Once you do that, we need to identify what are the tools that are needed to solve these problems, what are the algorithms that should be applied, and what are the mathematical constructs that are needed in solving this problem. That is what the step 4, which is method identification. Once you identify the method, we need to solve the problem using the method, using appropriate platform, where you really solve this problem and then see the performance metrics. That means, is your model able to accurately predict? If not, if yes, you are done, your data analytics problem is solved. If not, as we mentioned earlier, we will go to the step 3 and 4 and 5, and you will go ahead and then repeat steps 3 to 6. So as I mentioned earlier, this is an iterative process, and it will go on until you are satisfied with the models you are building and the accuracy of the final model. Next, we discuss an example problem to illustrate this flow of the steps in the data analytics solution of the data analytics problem. So there are readings from 5 sensors, F1, F2, F3, F4 and F5, that are made available for you. The data which I am going to show you in a short while, and we have 100 readings for all of these sensors. Okay, and then these readings are not arranged in any order. There are some records in which there are few missing values that are marked by NA. There are records in which there are 1 missing value, there are records which are no missing values, and there are records which are having 3 or 4 and 5 missing values also. So you have joined data analytics as a intern or something. So your supervisor has asked you to fill, you have any ideas to rationally fill these missing values. So what data analytic approach should we use to answer this problem is the question. So this is the problem given to you. Essentially you are given a data which is of 5 sensors and 100 readings. What is so we will take you through the step-by-step procedure which you have seen just now, and then we'll solve this problem to an extent, and rest of the problem you are going to solve as a project. So this is the questions that is being asked. Divide the data set into 6 groups, that is no missing, 1 missing, 2 and 3 and 4 and all missing. Based on the group where there is a no missing data, identify if there are any interrelations that can be extracted. If it is so, what are the linear algebra concepts that are useful in doing this problem? If there are interrelationships, how do you use those to answer the questions? So you need to fill up this NA missing values using some approaches which you are going to discuss. Okay, so what is the step 1? The problem definition. What is the problem definition here? We need to fill the missing data records which are noted as NAs. What is this what kind of problem is this? There are no sub problems. This is a small problem, so there are no top level problems, and we are discussing only one sub problem, which is a functional approximation problem. Why is it a functional approximation problem? Because given using the partial information that is given, we need to find out the missing information. That is relating the missing information with the known information, which is known as a function approximation problem, which is generally represented as x unknown, which you want to find out, is a function of which is the data that is given, which is x known. So we have seen step 1 and step 2. What is step 3? solution conceptualization. So simplest assumption one can make is this 5 readings of F1 to F5, we assume that they are independent of each other. That's the simplest assumption we can make. That means we can say that there are no relation that is existing between these variables. For each variable, we can fill the missing data with the most likely value. So if you assume that there is no relationship existing between these variables, what is the most likely value? The most likely value is the mean of the F1 for the missing values in F1, mean of the F2 column for the missing values in F2, and so on. So once you do that, you can average so the solution is average is the most likely value. That's the step 4. This is the method you are using. You are replacing the NA values by the average value of the elements in that particular column. That's the method identification. Once you do that, what is the fifth step? Fifth step is actually calculating the mean of these columns and replacing the NAs with the particular with the mean of the particular columns is the step 5. And if you are happy with that, and if you can see, you need to assess the assumptions as a step 6. So how do you test whether there is a correlation between these variables or not? You can actually do the correlation test and then see whether there is any correlation. If you find correlation, what is happening here? The assumption which you are making that these variables are independent is wrong. So what you have to do is you have to go back and then again to the solution conceptualization and then assume that there is variables are dependent on each other, and if they are dependent on each other, how do you use the concepts such as null space, which are taught in the linear algebra module of this course, to solve this problem. So once you do that whole process again, and you will end up with the values for NAs using the null space method. So this kind of illustrates the framework and one example of data imputation. How do you actually apply this framework in solving the data analytics problems? Next we move on to problem where we actually see the data and we will explain the questions that are needed to be answered for your project and what is expected from you in that project. The problem statement that is given in a Google spreadsheet. This Google spreadsheet will be shared to you. What you need to do is you need to make a copy of this Google spreadsheet, keep it in your drive and then work on it. The reason why I am asking you to make a copy of this because so when we share it with you, everybody will get rights to edit it, but if you start editing on it, every time it will get edited by someone else. Whenever someone else solves the problem, that will be getting replicated in this Google spreadsheet. So the reason why I am asking you to save a copy of this is the reason, save a copy of this and work on the spreadsheet, copy of spreadsheet. So this is the data. We have columns F1, F2, F3, F4, F5. These are the sensors which I was talking about, and there are about 100 readings we can see. So there are 100 readings and there are places where there are missing values. So for example, take columns row 6. Oh, this don't work on this browser, right? The pen works on browser? No. Okay. So example, see the column row 6. So you have 3 missing values, and in the column 7 you have 1 missing value, and so on. You are finding some rows that are having missing values represented by NA. The problem statement is to find out these missing values. There are different ways you can find out these missing values. The first question for the project is you need to identify the number of rows with no missing values and the number of rows with 1 missing value, with 2 missing values, and with 3 missing values and 4 missing values. Each of these questions will carry 2 marks and it sums up to 10 marks. The second question is you need to find out given set of, say for example, C6. So what is this? C6 is this is the cell which is C6. So you will be asked to find out 3, 4, 5, 6, 7, 8, 9, 10 values which are shown as NAs. This 10 can be anything. Okay. So you need to find out this 10 values using the mean imputation method. That means you assume that there is no relationship between these columns and then you fill out this NAs. What is the solution for filling this NAs? As we discussed earlier, if you want to impute a value for NA here, mean is the solution, most likely solution, which is mean of the columns, mean of the all rows in this column except this where there are NAs. So that's the solution. This is the question number 2, and the question number 3 is if you assume that there are linear relationships, interrelationships between this F1, F2, F3 and F4 and F5, what are these values of the particular cells that are being asked for? Okay, this Google spreadsheet with your elements that are needed to be filled will be separately sent to you after the course, and you have to work on this. So that kind of illustrates the framework for data analytics problems and an example of data imputation where we have this census readings and NA values, how to find out the appropriate NA values using 2 methods. One is mean imputation, the second one is using the null space approach, which Professor Raghu has taught in the linear algebra module of this course. So for answering question 3, your null space concept will be useful. For answering question 2, it's just a mean of the elements in the columns, corresponding columns, to fill out the null space NA values in the spreadsheet. So once you enter this particular value for C6 or D6, whatever you are being asked for, that will be entered into the system and it's evaluated automatically. That's the project evaluation. And if you have any questions on either the framework or the course project, which I am assuming there will be a lot of questions on the course project, I will be ready to answer those questions. So maybe we need to switch between the PowerPoint and this if they have questions on. I'm going to wait for 2 or 5 minutes to receive questions regarding the framework or the project statement itself. Okay, so if there are no questions, what we are going to do is we finally summarize the instructions for the project and finish this. So these instructions for the project are, you have to make a copy of your Google spreadsheet that is shared with you and work on the copy of the Google spreadsheet, and then you need to fill out the appropriate cells, which are, you need to enter the values for the cells that are being asked in the questions. Question number 1 is simple. You need to identify the number of rows with 0, 1, 2 and so on, how many missing values, with 1 missing value, 2 missing values, 3 missing values, 4 missing values and so on. And question number 2 is using the mean imputation approach, and question number 3 is using the null space approach. In this null space approach, what you have to do is you have to somehow extract the rows of the data set which are not having NAs and then calculate the rank of that A matrix. That will give you R, and N is the number of rows you have. So based on that and the conceptual understanding that we got from the linear algebra class of this course, you should solve the problem 3. So if you have any questions, I am happy to answer, and if not, we will wind up in 2 minutes. Okay, if there are no more questions, we will wind up. Thanks.